Okay, so today we're going to take a look at something that's kind of a classic problem. And it introduces the idea that, well, something that may come up in one or two of the types of problems that we'll take a look at. In particular, let's talk about this, a bathroom scale. Now, most people are kind of familiar with this. You set it down on the ground, and then you step on it, and it tells you numbers that usually fill you with rage, and then get you set up for the first of the year, so you can make promises to yourself that you won't keep, that you will change that. However, the question is this: what does that scale actually measure? Now, it's measuring a force. That's one of the things that we're going to talk about specifically, but what force does it measure? Now, today, in this video, we're going to take a look at something called apparent weight. And you may be wondering why this board isn't showing anything. That's because I have it frozen. There we go, apparent weight. Now in this, what I'm going to point out is, first and foremost, we want to try and get an idea of what the bathroom scale actually measures. Now most people's immediate response might be, and with good cause, that what it measures is the force of gravity. Well, specifically the force of gravity on me. The only problem is, I can step on it with only 1 foot, and I end up with something where, depending on how much I lean one way or the other, it changes what it is. Does that mean that the force of gravity on me is actually changing? No, I still have the same mass, and therefore I still have the same actual weight. Most people use the word weight to actually be the force of gravity. And that's why we're going to talk about something called apparent weight. How much it seems you weigh. In short, what the scale actually tells you. Now right now I've only got 1 foot on there and I'm leaning a little bit. There we go. I'm about 1/2 of the way, or of the reading, that it has when I step on here completely. So, the first and foremost thing to draw your attention to is these bathroom scales don't actually measure the force of gravity on you, not directly anyway. So here's what we're going to do. We're going to take a look at what it normally reads. So we've got the bathroom scale, and we've got a person standing on it, who's either happy or sad, depending on what the scale reading is, or maybe ambiguous. So, if we've got it where it's normally being used, say in a bathroom or on a lab floor or something like that, let's look at the forces acting on the person. Well, we have the force of gravity, Fg, and we have a normal force from the scale holding them up. Now, if the person steps off the scale, I didn't separate those out and I don't really feel like doing that, but imagine that the person steps off the scale, it now reads 0. Does that mean that gravity is no longer pulling on me? No, it means that, well, this would be my free body diagram, but it's from the floor. What we're actually getting, and you can check it like this too, take the scale, put it up against the wall, and push. And you'll find that you can actually get it to read something. What the bathroom scale actually reads is not the force of gravity, but the bathroom scale reads the normal force. If you're stepping off of the scale, then it doesn't have a normal force that the scale is applying onto you, and the scale reads 0. It doesn't mean that the force of gravity isn't pulling on you, or that it's got a very low value. No, it just means that that's not what the scale is actually measuring. Well, what good is it? Well, if I'm actually standing on the scale, then we'll find the following. If I'm simply standing there and applying Newton's second law, here's my free body diagram. We only have forces in the y direction, so I'm going to jump straight to looking at the sum of forces in the y direction equals my mass times my acceleration in the y. I get lazy when I split them in the y, and I don't always put the vector sign, but they are still there. The vectors are there, and we're going to talk about why that's important. Let's say that we're dealing with an individual whose mass is 50 kilograms. Now, that's another thing that I want to mention about this. In class, we've talked about it a little bit, but mass is something that you get just from the amount of material you get. So we can take me, and we could take me into deep space, and let's say that I have a mass of 50 kilograms here on Earth. If I were to go into deep space, I would still have a mass of 50 kilograms. I could be standing on Jupiter, assuming you can stand on Jupiter, and I would have a different weight. There would be a different force of gravity on me, but I would still have the same mass of 50 kilograms because I have the same material. The only way that I could reduce the amount of kilograms, the mass that I have, is to lop off an arm or something. I'd have to get rid of some of the matter that makes me up. If I wanted to increase it, I could eat some more, I guess, or maybe wear a backpack everywhere, or a fashionable sweater, if you will. And so the sweater's probably not going to add very much to it. Perhaps. I need a solid gold sweater. Anyway, the important thing about this is what the bathroom scale reads, well, it would read differently if it were on, say, the moon. But not because it's directly reading the force of gravity, but as we're about to see from the sum of forces on it. I do want to emphasize, however, weight is a force. It usually refers to the force of gravity, depends on who's using it, but it is always a force measured in, say, newtons or pounds. In the imperial system, pounds are the measurement of force. Now, mass is something that just deals with how much material is there. And the more material you have, the harder it's going to be, according to Newton's second law, to get the thing to move. If I were floating in deep space, you'd still have to push on me harder than you would on, say, a pet cat, for instance. You could get a cat moving by pushing it much less than pushing me because I have more mass. There isn't really a good equivalent in imperial. There are a few of them, or I should say, there are good equivalents, but most people don't actually talk in terms of them. The one that I learned in engineering was, instead of kilograms, in imperial you actually measure the mass in slug. And so there's a conversion on that. You could look it up online. I think stone, I can't remember if stone is a unit of mass or if it's actually, that may actually be just another unit of force. You're welcome to Google that and find a little bit more. But in short, mass deals with how much material you have. I'm always, if I have 50 kilograms mass here, doesn't matter where you put me in the universe, I'm always 50 kilograms. But my weight, how heavy I am, is as a function of the force of gravity. If I'm out in deep space, I'm no longer heavy. You could pick me up pretty easily because, well, there is no up there. You don't have to fight against gravity. Now that we've got that out of the way, let's take a look on flat level ground. If I'm standing in the lab or in my bathroom on this bathroom scale, my acceleration in the y with me just standing there, well, the acceleration in the y would be equal to 0. And my sum of forces would be the normal force, positive, minus the force of gravity, mg, will be equal to my mass times my acceleration, which in this case is 0. Well, that means that my sum of forces is equal to 0, and I'll quickly end up with this. Normal force equals mg, our force of gravity. Well, if we're on the surface of the Earth, on flat level ground, not accelerating, I'd have 50 kilograms times 9.81 meters per second squared. And we would go through, multiply those out. Let's go ahead and do that. Now we get 50 times 9.81. I would end up with normal force would read 490.5. We'll call it 491 newtons. That's what the scale would read if I had a scale that read in newtons. Now, here's where I'll remind you that 1 pound is equal to about 4.4 newtons. So that means that this, in numbers you might be more familiar with, is about 111.5, so maybe 112 pounds. Now, I'm using an example here. I'm a bit heavier than that, but 50 kilograms seemed like an easy number for us to work with. Okay, sorry about that. Camera cut out, unfortunately, so I've spent the last probably 10 minutes talking to myself. So, let's pick up where we were. As I recall, where we finished up was we solved what the scale would read on flat level ground. Now what we're going to do is we're going to see what happens if you're not on flat level ground. Let's say that we were to take this bathroom scale onto an elevator. Now, elevators, I get on them when they're not moving, and then they start moving upward with, eventually they'll come to a constant speed, but at least at the very beginning, they end up with an acceleration upward. So, my question is this: what will the scale do when we start accelerating upward? All right, so I'm going to say that we're going to have an acceleration of positive 1 meters per second squared. We're going to accelerate upward at 1 meter per second squared. All right, well, if I draw my free body diagram of me on the elevator while it is accelerating upward, I'd still have the same two forces, the force of gravity and the normal force. Now, I know a little bit about how this is going to turn out, so I've made the normal force a little bit bigger. It's a bit bigger than the force of gravity. We don't always draw things perfectly to scale, or even try to, but in this case, I'm going to go ahead and do that. We're going to apply Newton's second law, and I only have stuff in the y direction, so I'm going to jump straight to the y direction. My sum of forces in the y will be equal to my mass times my acceleration in the y. Now I get lazy, but these are still vectors. The reason that I know that they're still vectors is when we do this, you'll know from class that the normal force is positive because it's upward, and minus the force of gravity because it is downward. We're still keeping track of direction. Well, that's going to be equal to the mass times the acceleration in the y. We said for this individual, we're going to say that the mass is equal to 50 kilograms. And we want the acceleration in the y, which I said was 1 meter per second squared. Positive because it is up. All right. Pardon me. All right. Normal force minus the force of gravity, which is mg, equals 50 kilograms times 1 meter per second squared. We're going to find that the normal force minus the force of gravity equals 50 newtons. A kilogram times a meter per second squared gives us a newton. All right. I'm going to find that my normal force equals mg plus 50 newtons. Now, our mass is 50 kilograms and g is 9.81. We've actually solved that number before. That came up to 491 newtons plus 50 newtons. In this case, the force of gravity is still the same on me, but the scale reads something different because it is pushing on me harder than the force of gravity because it's the thing that is pushing me upward to accelerate me with the elevator, which is a good thing. So this comes up to 541 newtons, if I'm not mistaken. And then, if I take 541 divided by 4.4, we end up with, this comes up to about 123 pounds. I appear to have gained about 11 or 12, depending on how our rounding goes, pounds. Now, this is why we call it an apparent weight. Normally, when we say weight, we refer to the force of gravity on us, and I have not had my force of gravity on me change. It is still 491. But what the scale reads and what I feel has actually gone up a little bit. Now, when you're on an elevator, you actually feel this, even though you may not understand exactly what it is. You may not even think about it just because you may have gotten used to it. But when you press the button and the elevator starts moving, you feel squished just a little bit. Feels almost like you're being pushed down some. You're not. You're actually being pushed up, and what you're feeling is the normal force pushing on you harder to accelerate you upward. You feel heavier because you experience the normal force just like the scale does. That's what you actually feel. You don't feel the force of gravity, so as you jump through the air, you don't feel the force of gravity on you. What you actually feel is the normal force of you being held up. And since the normal force actually gets a bit bigger, your mind, your body interprets that as, I got heavier. You didn't. It's just that the normal force, what's pushing on you, is greater because we have to accelerate you upward. Now that's if you're going with a positive acceleration. Let's say that you are getting to the top and you have to slow down. You've got a velocity upward, and we're going to slow down so that we can actually get off on the floor that we want. That means that you need a negative acceleration, negative 1 meter per second squared. Now, this can also happen if you're getting on the top floor and going down. You'll have a similar effect where you're at zero velocity, and then you start accelerating downwards, speeding up downward. All right. In this case, we could say that we're slowing down. It's either way. I'm going to draw my free body diagram, and this time it looks more or less the same, although my normal force will be a bit less than my force of gravity. I know that because I know that I have to have a net force downward so that I have a downward acceleration. In this case, we have our sum of forces in the y equals our mass times our acceleration in the y. And we get the following. Our normal force minus the force of gravity equals the mass times our acceleration in the y, which is negative 1 meter per second squared. Negative because it's downward, and our acceleration is still a vector. All right, normal force minus the force of gravity, which we know is 491 newtons for our 50 kilogram person, equals 50 kilograms times negative 1 meter per second squared. We end up with the following. Our normal force is equal to 50 newtons. Let's see. Oh, I'm sorry, negative 50 newtons, I apologize, plus 491 newtons. Negative because -1 meter per second squared. Our normal force this time will read 441 newtons. It will read a little bit less. When I was accelerating upward, I appeared to gain about 11 or 12 pounds, depending on how you round it. And here, if we divide this by 4.4, we get to right at about 100 pounds. I appear to have lost 11 pounds. Did I actually lose anything? No, I'm still the same mass that I always am, but the weight, the apparent weight that this scale reads and that I feel is a bit different. Now, we actually end up with this. It looks like we've gotten a little bit lighter. This explains why when the elevator starts going down, you feel kind of like you're kind of floating a little bit. Or when it's slowing down, going upward, you kind of get that same feeling. This is the explanation for it. What you're actually feeling is the normal force. Now, another place where this actually shows up and is very pertinent, we'll talk about this in class, this is usually described in, say, g-forces, but if you think about a roller coaster, when you're at the top, if you go over this very quickly, right here, you start accelerating downward. And a lot of times when you're at the top of either a roller coaster or sometimes if you're driving quickly on hills in a car, you almost feel like you're kind of floating down. You feel like you're much lighter than you normally would be. Well, that's when you're accelerating downward and the normal force holding you up is not nearly as much because gravity is accelerating you downward. So there's less of a normal force. On the other end of that, when you're riding in the roller coaster, when you get to the bottom of a hill or a tight turn or something like that, you have a much higher normal force that is pushing you and accelerating you upward. You're going down and then you have to level out. So you have to have a positive acceleration to get rid of that negative velocity. This is why you feel like you're being pushed down into the seat. It feels like you are much heavier. You're not actually heavier. That's why we call it, that's why we call it apparent weight. It's not actually changing the force of gravity on us. It's not even changing your mass, how quote-unquote heavy you would actually be. It just feels different. And it's what the scale would actually read, which can be predicted by Newton's laws of motion. In fact, another thing that you could do is then you could use a scale to actually calculate what the acceleration would be. But this is apparent weight.